When you look closely at the surface of an exposed human brain, you are met with a visual paradox. Despite controlling every complex action in the body, the tissue itself is a uniform, continuous landscape of gray matter. To a surgeon's naked eye, a diseased tumor boundary perfectly mimics the healthy tissue surrounding it. The stakes of this uniformity are microscopic. Cutting just 1 millimeter in the wrong direction can permanently erase a patient's ability to speak or move their arm. Relying on sight alone turns navigating the brain into a deadly guessing game. The surgeons are operating in a vacuum, completely dependent on finding a reliable map. This 3D map represents standard pre-surgery protocol. Doctors use static MRI scans to plot a surgical route with mathematical precision. But biology introduces a complication. Once opened, pressure changes cause the brain to shift and swell, rendering the map entirely misaligned with physical reality. Doctors cannot correct this by relying on textbook anatomy, because every single human's neural layout is unique. To safely traverse this shifting terrain, surgeons rely on an extreme, counterintuitive solution, waking the patient up in the middle of the surgery. When static maps fail, the surgical team turns the person on the table into a live navigation system. This procedure is called an awake craniotomy. It is medically possible because the brain tissue itself entirely lacks pain receptors. With the patient fully conscious, the mapping phase begins. The surgeons ask the patient to perform continuous cognitive tasks on a loop. They might ask them to recite the alphabet or count numbers aloud. They could hold up pictures and ask the patient to identify the objects. Or they might ask them to physically move their arms and manipulate their fingers. This animated diagram illustrates the purpose of these rapid-fire tasks. By speaking and moving, the patient forces specific language and motor networks to actively fire with electrical signals. While the patient is speaking, the surgeon uses a specialized probe to deliver mild electrical stimulation directly to the exposed brain tissue. That tiny electrical pulse momentarily disrupts the local neurons, exactly where the probe touches. By combining the patient's continuous cognitive tasks with the probe's disruption, the surgeon creates a live biological circuit test. The surgical team is now relying entirely on direct observation, monitoring the patient's task performance while systematically probing the tissue. They are watching for a critical error response. It happens the exact moment a patient suddenly slurs a word, hesitates on a picture, or experiences an involuntary arm twitch. That interruption translates into pure geographical data. A break in speech or movement means the surgeon's probe has just touched the exact border of a crucial brain region. This top-down view shows the surgeon's immediate reaction. They physically mark the tissue, outlining a strict no-fly zone around the critical function. This process is repeated millimeter by millimeter around the entire pathology, allowing the surgeon to map the safest route to the disease. The patient's active consciousness provides the only mechanism capable of drawing a definitive line between expendable tissue and essential human function. Through this real-time navigation, surgeons successfully remove the maximum amount of diseased tissue while ensuring the patient's essential motor and language functions remain perfectly intact. If a surgeon attempted to navigate that exact same path blindly, the resulting physical and cognitive damage would likely be catastrophic. In the context of an awake craniotomy, consciousness serves as a highly calibrated medical instrument.